Good morning, all. Good morning all to all the participants. Today, our speakers will join within a couple of minutes. You are joining the platform now. Just wait for a couple of minutes and we will share it as soon as possible. Sir, good morning, sir. Sir, good morning, Bhavan, sir.
Just 1 second. Huh?
Sure, sir. Sure, sir.
Let me also start video. Got it. इसलिए वो जो शेयर करना है ना, शेयर एक्सेस देने के लिए बोल. Now you have to give us the share access.
I give one, sir. I give it. So,
Right.
sir, already it's late. Can we start? Shall we start?
But this process, now I have to screen one. इसमें सर यही नहीं वो PDF है. PPT presentation PDF.
हाँ इसमें ये वाला है सर PDF वाला यही होगा यही है ना तो आप इसमें जाइए
नहीं
ये शेयर क्लिक को
Yes, are you able to see this presentation?
Sir, not. No, it's visible, sir. No, it's visible.
Are you able to see?
Yes, sir. Just zoom it, sir. Little bit. You zoom it. It is PDF format, right? Power.
Zoom.
Full screen.
ये वाला ये वाला
Right?
Sir. No, it's fine.
But
Solution, sir.
am I audible also?
You're audible, sir.
Okay.
So, with your permission, sir.
Even that doesn't matter. How many participants might be there?
Now it's 65, 61. So, Namaste, good morning all. On behalf of NIDM, I am Gautam, Joint Consultant at GIS and EOC. Welcome you all to the second day of a 3 days online training program, observing geohazards from space, organized by NIDM. Before we start our today's second session and the second day of 3-day online training program, I could like to convey my sincere thanks to Sri Tajasan IPS AD and Professor Surya Prakasa, Head GMR Division and CBRN, Industrial and Cyber DRR Division, NIDM, MHA, Government of India, Delhi, for giving this opportunity to conduct this 3 days online training program. Without late, I will recap our first day sessions. In the first day sessions, Abhinav Shukla, scientist SC at NRSC ISRO, has given the brief about the power of space technology in monitoring geohazards, followed by Amanpreet Singh, scientist SC, Flood Modeling Division, Disaster Management Support Group, NRSC ISRO, has detailed a brief about the flood inundation modeling. So without late, I'd like to introduce our first speaker to our audience. Dr. Ismohan Bahugavan was born in a village of Bhagani district of Garhwal in 1962. He is present working as a scientist as a Chief and Deputy Director of Earth, Ocean, Atmosphere, Planetary Sciences and Applications Area of Space Application Center, ISRO Ahmedabad. He had his higher education studies in a Center of Advanced Study in Geology of Punjab University, Chandigarh. He joined SAC in the year 1987 with overall more than 35 years of experience in remote sensing research and applications. He has contributed significantly in Himalayan cryosphere studies, especially on Himalayan snow cover changes, glacial changes, and glacial mass balance studies. He has described more than 60 research papers published in reported journals. He is a recipient of ISRO Team Excellency Award for 2008 for his contribution in Himalayan snow and glacial studies. With this, I'd like to invite Dr. I.M. Bhagwan, sir. Sir, the floor is yours, sir.
Okay. Thank you, organizers of NIDM, and for inviting me to deliver this lecture to the trainees of NIDM. In fact, I'll start with this, that there is, no difference between you and me. The only difference is that we are only sharing the experience. You all also have the same level of, experience, knowledge, etc. But I'll share the experience that what I had in the previous years. We are talking about geohazards, observing geohazards from space. Number one, from space, not only geohazards, but you can observe many more things, right? Geohazard is one of them. Now, by geohazard, what we mean? We mean so many hazards which happen on the earth. It may include atmospheric hazards, it may include all hazards related to land, all hazards related to oceans, and you may be aware already that what type of hazards are there. All come under geohazards now because geo means earth. So, like for example, floods, etc., heavy rainfall, cloud burst, they are all atmospheric. Then hydrological is flood, etc. Then sometime, these tsunamis, etc., happen in the ocean, then on the land, landslides, etc., and happens in the glaciated terrains. So I'm not saying that I can cover all the geohazards, but by giving example of two geohazards, what we will try to convey is that, am I audible to all of you?
Yes, sir. Yes, sir.
Okay. So by conveying the methods and approaches of using these two, giving examples of these two hazards, what I'll try to convey that how we should use the space-borne data for geohazards in the geohazard application. That is the message I want to give. Now you may be already, before I switch over to actually geohazard to GLOF. GLOF is glacial lake outburst floods. When a glacial lake burst, you must have heard many such glacial lakes have bursted. But let me tell you that all are not glacial lake, all are not typical lakes which make the region hazardous. All the lakes do not make so. But what are the reasons why people are saying that glacial lakes are bursting? That is it really the data says that? I'm not sure about it. That the data indicates that recently so many glacial lakes outburst floods are going on. Earlier also they used to be, but earlier the communication was very less and people did not know what is happening in the high altitude region. So that may be the reason that we did not know, but now we know about, we have mobiles, etc., to click the video and everything, what is happening in the high altitudes. And moreover, people have reached to high altitudes for economic reasons. So, as far as globes are concerned, people say that, scientists rather say that because of climate change, glaciers are melting very fast, snow is melting very fast. So, as a result, the melt runoff creates GLOF or say glacial lakes. These are all, such kind of processes where one can think of this. But is it really correct that this is happening? Huh? So, for example, we will take example of, say, for example, Kedarnath disaster. In the Kedarnath disaster, there was a cloud burst for 3 days and heavy rainfall. So that created a lot of rain. Then that rain created a lot of melt on the snow because rain has higher energy than snow. So it imparts energy to the snow, and then there was a lot of snow melt. Then that snow melt and rain was flowing. On the side of a glacier, there was a lake, and the mouth of the lake was very, very narrow. The sediments choked the mouth of that, and a lake was formed, and which also, along with the heavy rainfall, which also busted. So, point is that it was not a typical glacial lake. Now, it was associated with glacier, but not a glacial lake, which are found on the near the snout or in front of the glacier. Now, what is happening for this? We also make, in the Himalayan region. This is one image showing the Himalayan. There are various lakes. Depends on the scale of mapping that how many lakes you are able to see. We are monitoring snow cover for the last 15 years. And snow cover also depends on the latitude of the basins, and based on, if you see the altitude of the basins, you find that altitude wise there is no, except in the Nepal region the altitude is slightly less, but in the eastern Himalaya and the western Himalaya the altitudes are high, right? Similarly, latitude wise, if you see the Himalayan region, latitude wise it is decreasing. It has altitude and latitude control the snow as well as the glaciers anywhere in the world, anywhere. That is why in the polar regions you find snow and ice at the very low altitude. But in the mountains, in the tropical regions, you find them at a very high altitude. It is the combination of altitude and latitude which control the occurrence of snow and ice. So, in Himalayan region, we have been monitoring. So, what is the fact? The fact is that if we see annually, These curves show, these cover almost all the major basins of Himalaya. These trend lines show that there is not much change in the snow cover in the Himalaya if we take the average snow cover. Average snow cover. Annual average snow cover, we don't find any much change in the basins, right? In the snow cover. But that means snow cover is not changing. But if we analyze the snow cover data monthly monthly average, we find there is a decrease in the snow cover in the time of October month. That means the snowfall has delayed. It is getting delayed. What used to be snowfall in October, now that is not falling. So there is a decrease in the snow cover in the month of October. That is what is happening. So slowly and slowly it might go from October to November to December, like that. Months of snowfall might reduce. So this is the one example of snow. Now another example you will see, I will show you some images of glaciers in Himalayan region. This top row, these are small glaciers. First glacier of 1989 is covered with snow, but it is appearing in blue color because it is covered with snow. Now in the second, in 2001, it is not covered with snow, only the upper part is covered with snow, but lower part is exposed, ice is exposed of the glacier. Then in the third again it is covered with snow, and fourth also it is covered with snow, because they are very small glaciers and located in very high altitude region of Himalaya. So they are covered with snow. Very rarely you get the image when they are not covered with snow. But if you see the size of these glaciers, it is not much changing. Do you find any much change in the shape of the glacier? 1989, then 2001, 2011, 2016. Do you find change here? So what does it mean? That small glaciers are not responding to the climate change. But after seeing few glaciers, we find that why there is no change. There should be some change in the area, etc. But we cannot, image cannot belie anything, right? So in the second row, you find another very big glacier. This is Bada Shikri Glacier, which is covered with debris. And on the side of this Bada Shikri Glacier, there are small glaciers, which are called as tributary glaciers. So these glaciers, this is debris covered. Debris covered means over the glacier, there are rock debris. So you cannot see the ice directly. As you see here, this is the blue ice. This is the blue ice, you can see directly. Here, this blue ice is covered with snow. Here also they are covered with snow partially. But here this main glacier, Bada Shikri in Himachal Pradesh, doesn't appear to be covered with snow. So it is covered with debris. Debris means rock debris, which is the most important thing for any formation of a glacial lake in front of a glacier. Now third row you see, this is a lake in Himachal Pradesh in 1989. Now this same lake in 2001, 2011 and 2000. This lake, the surface area of this lake has increased. It is in Himachal Pradesh, Gipangat Lake. It is called as Gipangat Lake. If the surface area is increased, it means also the volume might have increased, definitely. And wherever there are such lakes, they will further retreat the glacier. They will reduce the ice. They will eat away the ice. These lakes will eat away the ice and reduce the size and surface area of the glacier. So wherever there are lakes, the glaciers will be found retreating. Obviously, this is a obvious reason that the water is not as frozen, so it has more heat than the ice. So it will melt the ice. So these are the lakes which are increasing. So does it mean that this lake can burst any time and create a flood, glacial lake outburst flood? Why it has not created so far? If it is so, like this, there are certain questions. So such questions also arise in case of all the glacial lakes which are in front of the glacier, right? So now if I show you how much is the glacier retreat. how much percent is the change in the glaciers. So at Space Application Center, we have mapped about 5,225 glaciers, and out of that, we have measured debris-covered glacier, debris-free glaciers. Like that, we have classified them and found that what is the percentage of change in the glacier area in the last 15, 16, 17, or say you can say 17 years. So we find that in, say for example, in Sikkim, the change is minus 2.15%, plus minus, that is uncertainty. Then in Nepal and adjoining region, this is again 2.16% in the 17 years, percentage wise. In Uttarakhand, it is only 0.84. In Himachal Pradesh, 2.22. In Karakoram, this is hidden before another window. Yeah, anyway, in Karakoram, the change is almost nil. That is, in fact, it is plus in Karakoram. Karakoram is the POK side of India. So, point is that this is the rate of retreat of glaciers. Now, if it is the and total, if we calculate, it comes out to be 0.54% area change in the glacier surface area. Now, this is the change, and glacier area does not change immediately. It takes a lot of time to change. These are the results of snow and glacier mapping, which are very important to know the law in any region. Now, next is that if we see the temperature of in the Ganga basin, the temperature has been rising slightly in the month of June. Then in July, it is almost stable. In August, average slightly increase, and in September, the trend is slightly increasing of the temperature. But in Indus basin, Indus means which goes to Pakistan through 5 rivers of Punjab and Jhelum, etc. So there you find that there is not rise of temperature much or significant rise, but in Ganga basin there is rise. That is why you find more retreat in Nepal and Uttarakhand region than in other region. And if we see the glacier retreat, we find that in higher latitudes, the retreat is less. In the lower latitudes, the retreat is high, because in lower latitudes, the temperature is higher than in the higher latitudes. So this is the basic reason. Now, all these things I am telling because so that you can understand what are those conditions which create Gloff situations. But now, if it is so, then we had mapped some glacial lakes of Nepal and Bhutan long back from the data of 1990 of Landsat and AWIPS data of ISRO. So we are trying to map all the lakes, glacial moraine dam lakes. I am not talking about the glacial lakes, but I am talking about the moraine dam lakes or the pro-glacial lakes. What is the difference? Now, before I go to that, let me tell you there are 5-6 reasons for the formation of lakes in the high altitude region. One is snow melt. Second is glacier melt. Glacier melt is not important. Snow melt is not important. Important is sediment load which comes down. That is important along with the water. So that is one of the reasons. Then the reason is for the formation of lake is groundwater which comes in the depression. Slowly groundwater moves below the surface, and wherever there is a depression, it emerges out, and the lakes, beautiful lakes are formed in that. Now, also lakes are formed whenever there is a landslide or any activity, such activity, avalanche, etc., which can choke the channel of water and create a temporary lake. That is also one of the reasons. Then another reason is that in sometime we make we do some construction work, etc., and so sometimes the debris of that can choke the channel. But there are two important things. Now, one is that whenever there is a lake formation in the Himalayas, and any lake is being formed, and suppose we see using satellite data, we should always see one thing, that the valley is not narrow. If the valley is narrow, very narrow, and the discharge rate is very high, then there is a chance of blockage of channel, and a temporary lake can be formed, as it happened in Kedarnath also. Now, if suppose the channel is, of course, channel is not big, but the valley is very wide. Suppose, as a valley of Satopan Glacier or Alaknanda Basin near Badrinath, it is a very wide valley. So even if it is gets flowed, suppose temporary, whether there is a chance that water will be stopped, water can move from sides, water can go from sides. So there is a less chance, and a valley which is, say, suppose half-kilometer wide. Is it possible that immediately overnight a dam can be formed? No. But in a very narrow channel, when there is a channel is very narrow, very high slope, and the water discharge is very high, there is a chance that a temporary lake is formed which can stop water, and because of rock fall or landslide, etc., or avalanche, a temporary lake can be formed which can stop water for some time, and when the pressure of the water will increase, there is a chance of the bursting of the lake. So such situations are very important. So we have tried to see moraine dam lakes. Moraine dam lakes are called as moraine dam because moraine is the rock debris which comes along with the glacial melt. That is called as moraine. So many times what happens, that when the moraine comes down, it gets accumulated and it can create a temporary dam. When that temporary dam becomes bigger and bigger, lake gets increased. But if suppose water goes out of that dam slowly, seepages, then there is not an issue. But suppose water gets choked by the dam and the dam bursts, then there is an issue. So we had measured, mapped pro-glacial lakes and moraine dam lakes. Moraine dam lakes in Bhutan and Nepal, and we found that yes, of course, no new lakes were formed, but we found that area of the moraine dam lakes had increased, and it was, say for example, the total increase in area of lakes was found to be 424.43 hectare, with a mean increase of 10.48 hectares. So this was the total increase in the surface area of the lakes. So of course there is a effect of climate change on the volume increase and area increase of the lakes. We also observed that these are two. This is the lake, one in Nepal, and it is we are seeing these two lakes in two different data sets, 1989 and 2005. AWIPS image. This is the lake. You can see it is in the frozen state. Why? Because all lakes in Himalaya remain in frozen state for most of the time. Only on a few months, for say July, August, September, when there is a rainfall in summer, the lakes can melt and become water, and then only there is a danger. But most of the time, all these lakes are frozen and so cannot burst, right? So we need not to worry throughout the year, only during the time when there is a melting of frozen ice in the lakes, then only we should worry. This right side, this analysis of the shows that wherever there are lakes, the retreat of glacier is higher, loss of glacier area is higher. Where there are no lakes, the glaciers have not reduced in their surface area. So what lake does? Lake further enhances the reduction or increases the rate of retreat of the glaciers. So that is the double effect it causes. So this was one of the study. Now we go to another case. This is the lake in Sikkim, and this was, I had already told, Kepangat Lake, which is increasing. And this is the 1965 corona photograph where lake is again seen. So lake has definitely increased, but not busted, right? Now, what are the different models which are used to predict the probability of the lakes busting? So some model which is published is the equation is given here. McKillop and Clegg 2009. They say that on the left hand side you can see that one of the image shows that lake is frozen. This is not water. The lake is frozen. So this is the frozen time image of the lake. So this model shows that if you consider geology, lake area, ice core, and height ratio, and like that, you can they have made a model to predict the probability of probability of busting of the lake. Yeah, this MHW is moraine height to width ratio. Now, these are some of the parameters which they have considered that they can say, and they say their model is very good. But let me say that whether whosoever produces any model and whatever models are there, but one thing is there, we should always use our own common sense also while studying anything. What is that common sense? That if the lakes are there and expanding, and the valley is very wide, then we should not worry much. I don't say that we should never worry, but those areas where lake is formation is there, but the valley is very narrow and highly slopy, there is a chance that sometimes, suppose tomorrow cloudburst happens, or suppose heavy rainfall happens, or suppose landslide happens, or suppose avalanche happens, that may choke the valley and a large lake can be formed. So what we should do is we should map the entire Himalayan valleys and the existing lakes. We have also mapped at the Space Application Center high altitude lakes of Himalaya, and this work is also done by National Remote Sensing Center, Hyderabad. They also map the water body or the lakes of Himalaya. So similarly, we had done as a part of wetland, national wetland mapping, and we have mapped all high altitude lakes. So total 2627 lakes were mapped at 1:50,000 scale, and we found that what is the total increase in area of these, maps of high altitude lakes. 8955 hectare area has changed since last mapping of in the high altitude lakes. So definitely the lake area, the lake volume have changed, and it indicates the effect of climatic variation, climate change. Now, some lakes have also disappeared, and some new lakes have also been formed in the Himalaya. That it does not mean that they are all glacial lakes. They can be lakes of other sources like snow melt, like simple drainage coming from rain, etc. It can be anything, right? So the lakes which you find in Tibetan Plateau or in the mouth of the glaciers in Bhutan, Nepal, etc., they are formed much before the present age, and formed because of the melting and the depressions over there. In those depressions, such lakes have been formed, right? So I move further. Now, some people also, when they map lakes of Himalaya glaciers, what they do is they map all the lakes, with the lakes which are very small and lying on the surface of the glacier, what are called as supra glacial lakes. They also map those lakes. But are those lakes really harmful, or they can create, trough-like conditions? It is very difficult to say, because such lakes, when they melt, their water goes down below the glacier. It does not go down. So on the glacier, if the lake is, lake is busting, but normally such lakes will not be very big on the supraglacial lakes. They will be very always small, because if you can see the what is one example I am showing, what is the area of these lakes? Area is varying between 0.2, 0.25, 0.1 square kilometer, very small area. And these lakes are being formed. Sometimes they are disappearing. Again, they are formed. And the area is, when the area comes down this, that means lake is disappearing. Again, lake is formed and some increase in the area. So point is that those supraglacial lakes are not very significant from those point of view. Lake should be very big. It should be in the, in the narrow valley, and the discharge should be high if it can be treated as a strong candidate for Ground condition, right? So I'll come to your question, which might be, going in your mind by listening that what happened in the Rani or Chamoli last year. Definitely come to that point also. Another example where Himachal Pradesh government has mapped glacial lakes, including supraglacial lakes as well as moraine dam lakes. So they have mapped and they found that in, just 1 second. Hello. Okay. And yeah, can we talk after a few minutes, because I'm just on giving an online lecture to National Institute of. I'll call you. Okay. So this is now they have mapped lakes of glacial lakes for 3 years, and they found that yes, definitely the small lakes have increased, and this is the status. Presently, it is not necessary to know what is the status and how many are increasing or decreasing for you, but you should understand that what kind of mapping or the capability of images have to monitor such lakes in the Himalayan region. Had there not been any satellite, had there not been any images, could you see that those lakes in the Himalaya in high altitude? They would have been out of your visibility, out of the man's reach, and we would not have come to know what is happening to those lakes. That is the advantage of space-borne systems in monitoring of such lakes. Now here these are 2 examples. The top one is Dipangat Lake on the image, and this is the ground photograph of that lake. Now here the channel is very narrow. It can get choked, definitely. And the mountains are very high, and so a big lake can be formed. So far it has not formed, or the channel is not choked, that is a different thing, but it can happen. So government has to take care of this. Then another lake is Samudra Lake, and this is another glacier in Chandra Basin in Himachal Pradesh. But if you see this lake, this is the lake in image, and this is the lake on the ground. If you see this lake, I've seen this, both the glaciers, both the lakes. Now, if you see these lakes, this is a very big lake, and the valley is very wide, more than I think more than 1 kilometer wide, and glacier is also big. So, is there any chance? And this is a depression. This is a depression, or the depression on the surface where a lake has been formed, where the water is getting accumulated. But do you see the possibility of damming of this lake? But I don't see the possibility, because the channel is very narrow and water is going, and it requires a very big dam to stop the water. Very big dam that will not be formed immediately. It can get formed when there is lot of landslide of land, but that also. So, we have to see how much is the volume which is required for formation of a dam anywhere, and how much should be the landslide or the avalanche, etc. All that analysis should be done before we conclude that which are the lakes which can harm and which can create bluff-like condition and which cannot, right? A lake was formed long back in 2004 in border of Himachal Pradesh and China, that it was called as Peruchu, and a lake was formed, and it created a lot of panic. But after that, it automatically, naturally, released its own water. So the danger was over. Now, this is a case of rainy disaster, Chamoli disaster, which happened on the 7th February last year. Now, when this disaster had happened on that day, that was Sunday, and we were hearing from the WhatsApp and the news channels that a glacier has, what do you say in English? I don't find any suitable word in English, but in Hindi, it was coming in the news that a glacier फट गया है. ग्लेशियर फट गया है और ग्लेशियर फटने से इतने लोगों का ये हुआ है ऐसा. तो बाय गोइंग बैक टू माय नॉलेज ऑफ ग्लेशियर्स एटसेट्रा, आई थॉट व्हाट इज दैट कंडीशन जिसमें ग्लेशियर फट जाता है. ऐसा क्या ग्लेशियर फटते हैं? और देन आई आल्सो थॉट दैट अगर इफ इट हैपेंस रियली, देन all the glaciers which are lying on the slopes of the Himalaya would have come down. Why they are lying there? They are on the slopes. Why they are lying there? So all these questions were coming in my mind. That then I saw on the same day, I saw the previous image of that region, and I observed that the valley is very narrow and highly sloping. Then by evening, we had come to know from some other sources that some rock piece, of the very high, big size, had fallen down. Rock had fallen down, right? Now, when the rock fell, it had, broken down into small pieces, and it had fallen from very high altitude, maybe 500 meter or 1 kilometer altitude. All the rock mass had come down. That was not an avalanche. You can call it a rock avalanche if you want to say. But avalanche term is given to snow avalanche. So that rock had come down, and it brought with its mass some dying ice aprons. Those ice masses which lie on the mountain, but they are not typical glaciers. They are not typical glaciers. They are rock masses, the ice masses which are hanging on the slopes. The glacier is here. This is the glacier. Are you able to see my cursor? Hello?
Yes, no, yes, sir, yes, sir.
Can you see the cursor?
Yes, sir.
So this is the valley glacier. This is a typical glacier. But all over the mountains, you will find that these are the snow masses. When snow remains there for a long time, it gets slightly converted into ice, and those ice masses are lying on the slopes. So rock had fallen, it brought down some ice mass also. And it must have choked this valley here. Definitely, it will choke the valley. Now, in the month of February, the discharge of the glacier is very less, because it is a cold time in high altitude. You cannot stay there. It is such a cold, time. So, it must have stocked some water. But whatever water is coming, very little water from the melt of the glacier, that must have taken some time to accumulate because of the choking of this valley. So when this came, some water got accumulated, and some water was formed due to melting of ice which had come down along with rock. And rock also got into pieces, so a lot of sediment was produced. All together, mixing of these 3 points must have created a slurry of debris covered water. Otherwise, water comes down very coolly. If there is no disturbance to any valley, the water flows down, and it is so transparent you can see that bottom of the stream. But when you disturb it, then sediments must have come down along with it, which went into the tunnel of hydropower station and choked all the, the people who were there, their throat and nose, and must have been choked with the water loaded with the sediment, because they did not have time to come out. So that was one of the reasons. So it is not a typical case of glacier lake, etc., but such kind of situations also can. Disaster has given us a view that such kind of disasters also can occur in Himalaya. This is a new type of disaster, right? So we have to be prepared for such, regions. Now, this is Kedarnath. I don't need to discuss it. We have already discussed it. Now, this is during the rainy disaster or the Chamoli disaster. We had done some analysis of the snow cover. Definitely, the snow melt also had increased on that day because of higher temperature. That was also one of the reasons. Now, we will go to this. Now, in order to model glacier lakes, see, on that day, when we were analyzing this event, without knowing anything, without knowing, going to field, without, I had written this in the evening to be sent to my higher ups, my bosses. What I have written, see, we have not observed any glacier lake in front of all the glaciers in the region. However, further checking using recent high resolution data is desirable before conclusion. I don't conclude anything so fast. Extreme rainfall or cloudburst can also trigger the flooding. However, inset images in MOSDAC and forecast do not reflect such events. We are also suspecting avalanche along with debris flow mixed with dead ice of the glacier. We are waiting for the post-disaster. And I have written, normally glaciers are intact bodies, and breaking of a glacier is rarest of the rare event. If it has happened, we have not come across such breaking earlier. These are my words on the same day of the event. And later on, whatever papers were published on this topic, they also said the same thing, right? So we have to apply some, logics, common sense, etc. Anyway, GLOF, to monitor GLOF, you require models, and which means that you should take care of inherent characteristic of the valley and the meteorological conditions: heavy rainfall, cloud burst, snow melt, glacial melt, avalanche, temperature, and also the ground condition like earthquakes, ice cold moraine, landslide, degradation of dam wall. Then only you can create a good model for the dam breach and for the GLOF. Analytical hierarchical process are also used for such things. Now, we have tried to parameterize some of the things like glacier morphological parameter, glacier area, glacier average slope, glacial debris cover percentage, rate of change in glacier extent, glacial volume, lake area, lake narrowness, lake lambda, rate of change in lake extent, lake elevation difference. These are the ways in which we try to see that these are the parameters which are important to be known before we say anything about the GLOF condition. They should be mapped in the Himalayas, and a vulnerability map should be generated which says that this valley is more vulnerable to GLOF condition than that. Suppose you only monitor those lakes which are existing in front of the glacier, they might not, or they might or might not burst. So we have to see also that some new lakes are not formed, which can create havoc. So existing lakes and the new lakes. And existing lakes, if they are formed in the depressions, then we have to see how much is the valley width, etc., before we conclude. Now, these are the an early warning system which should be developed so that people are forewarned. What does it require? It requires inventory and monitoring of snow, glacier, high altitude, glacier and non-glacial lakes, lake area and volume, snow glacier melt runoff from the catchment, satellite weight derived geometric parameters using DEM, heavy rainfall monitoring, in-house developed, like these things. There are so many points which which are required for monitoring of the block condition and blocks in the Himalayan region, such as the these are some of the things. Now I'll just quickly cover landslides. Landslide, as you know, what does landslide means? Landslide means when land is sliding, right? Why should a land slide? Land can slide because of various reasons. That if the slope has very loose material, then also land can slide. If the rock fractures because of earthquake or any fault or anything, and rock mass comes down, that is also landslide. If suppose there is a heavy rainfall and heavy rainfall creates any lot of mass of debris, that is also can cause landslide. If there is a subsidence somewhere, that can also cause landslide. If suppose there is a avalanche or anything, that can create some landslide, etc. But normally what we say, in the lower altitude region we call it landslide, but in the very high altitude region we don't call it landslide, because landslide do not happen there, because rains are not there. There it is always snowfall. So avalanches are there, rock avalanches are there. They are also called as rock falls. Rock break because of heating and cooling effect throughout the year, frost action. So rocks break, that are rock falls, they are called rock falls. But landslide happen mostly in the regions where there is a heavy rainfall, like Uttarakhand, Himachal Pradesh, Nepal, Bhutan, etc., Sikkim, etc. Now, as we know that landslide and also landslide happen in the Western Ghats of Himalaya, of India, and there also you will find a lot of landslides, and it is a very important geohazard for which we should work together to mitigate such things, and we should think of developing early warning system for the landslide. I've seen many hundreds or thousands of papers have been published on landslide and describing the various methods and approaches and how satellite data has been used for landslide mapping and vulnerability mapping, etc., etc. But I have not much seen one thing in those papers, that can blasting of rocks for the development of roads, etc., cause weakening of the rocks and also create landslide. That part I have not seen, and in my view, that is also should be one of the parameters in any landslide studies, right? Besides rainfall and geology. Now, second thing is, just quickly finish. Now, these are some. If we are talking about landslide without seeing such photographs, our purpose will not be over. These are some of the photographs I have taken from internet, and these are showing some of the landslide in Himalaya, Western Ghats, etc. When landslide can be small and it can be very big, and particularly rains, and people have constructed house on the slope, but without knowing what is the underlying lithology, etc. And sometimes roads are there and landslide is occurring, and see how this car is got turtled down. So like that, there are various landslides which occur near the roads, and roads can break and vehicles can come down. And so these are some of the photographs, but of course we are not talking about only the photographs. I'll just show you one example of handling landslide matter. This is I'm also part of this work, and main author of this work is Ajanta Goswami of IIT Roorkee. So we have taken one example of Dharamshala area in Himachal Pradesh, where there are various faults, geological faults. Faults are, what is the fault? Fault is, where there is a displacement of the rocks along a line, along a fracture, that is called as fault. So there are numerous faults in Himalaya and also in Dharamshala. So what we have taken Dharamshala area. We have tried to map the landslide on the image and for this Dharamshala region, and some landslide are also available, information available in the website of GSI, Geological Society of India, and from there also we have taken. Now, using this, approaches, what we had done is we had divided the entire process of methodology into various generation of various indexes or factors: lithological factor, fault distance of the location, drainage distance of the point or landslide from the drainage, then from the road, from the what is the land use land cover, what is the DM, what is the slope, what is the elevation, what is the slope aspect, etc. So all these factors were parameterized to form a map-like feature. For each factor there is a map. Now all these maps are subjected to analysis in ArcGIS, and there are three basic approaches which have been used to the weightages are given to these maps, weightages to these factors. Now, these weightages can be analyzed by many methods. So, for example, the most used methods are, for example, are just tell me. Okay, it's not written here. Anyway, the weights are assigned to each parameter, and they are used in GIS conventions to find the correlation between the occurrence of landslide, the landslide which are already there, and what is the, based on the weightage, what is their correlation with this the landslide. Now, based on that, there are, by when you give weights, there are various ways of giving weights. They are different. That is a statistical method, and based on that, you are generating a vulnerability susceptibility map. Now, three major methods of giving weights and generating maps are info value, okay? Now fuzzy logic, etc. And using these methods, you are generating a landslide susceptibility map. Now, once your map is generated, you are trying to relate that with the landslide occurrence. And for that also, there are methods. One is a frequency ratio assessment method, and one is known as ROC method, response operative curve method. So, based on that, we try to analyze. It is not necessary to know what is the result of this method or that method, but by using this, you can know what are the various factors which are causing this landslide to occur in that area. That is the purpose of doing entire exercise. Now, once you know, then you can think that you can apply that to various areas of landslide. That suppose we apply this approach, whether we can generate landslide susceptibility map, and those locations which are very high susceptible, or you can say vulnerable to landslide, those areas we should concentrate more than those areas which are not. So basically, the space images or the work reduces your efforts and narrows down your focus, and you can focus on a small area where it requires more your attention than the entire region. So fault, roads, topography, wetness index will come from rain. So these are, and now recently you may be knowing that in SAR interferometry or the differential interferometry, where you try to monitor the movement of the masses. So on those areas which are narrow, in those areas you can use SAR data, and SAR data, because it can penetrate through clouds also, so there will not be problem. And using SAR data, you will find which are the areas which are moving. That means already in the motion. There, the chance of landslide is more. So that is possible using SAR data today. And some people have also studied this Chamoli disaster area using not SAR data, but using optical data, and try to find the deformation or the movement of the rock masses in the last 3, 4, 5 years. And they found that yes, it was moving. So such kind is the potential of satellite data. You can, on all these maps, whatever you are seeing, they are generated from the space images, land use, land cover, topography, to wetness, inlets, etc. And based on this, sorry, you can generate such kind of maps and then narrow down your area so that you can concentrate more in that area and use that SAR interferometry or DNSAR to monitor the movement of the masses where there is a more chance of landslide occurrence. That is the way. And with these words, I will now close my talk. This is not, one talk is not enough to discuss everything, but this is only to show you some, some idea. This is to only to give you some idea that these are the various things which are going on using space-borne images for geohazards. But for details, you need to study the books, the papers, you need to do the work, and all those things are required. But by just listening one lecture, we cannot understand everything. Even I also cannot understand. I have given this lecture, though I have not much work, but slightly but on that side, I have definitely contributed, but not as much as in glaciers. But in glaciers, I've been working for the last 3 decades. So then only I'm able to speak something before you. So it requires some time, to understand the entire system, the entire, uh, process of glaciers. So with these words, I thank my own director of Space Application Center Ahmedabad, Shri Nilesh Desai, who himself is an engineer of international repute and has worked in the area of radar development for the country. RISAT and 1A and 1B radars have been developed, his contribution. And then I also acknowledge and thank authorities of National Institute of Disaster Management, then colleagues of my Space Application Center, Dr. Ajanta Goswami of IIT Roorkee, Dr. Randhawa of HP Council of Science and Technology, and I am also thankful and I acknowledge the entire audience which has given me patient hearing for the last 1 hour, but your work is still not over. Another person, my colleague is on the line, so you will not be able to get a break, and he will start his lecture immediately after me. And thank you very much for inviting.
Sir, thank you so much for taking time for us to deliver the training session on observing the geohazards, especially emphasizing on the landslides and bluffs. Sir, with your permission, can we take a questions from audience? Sir, am I audible?
Yeah. If anybody wants to ask, please.
Only one question from the participants, sir.
Where is the question? Is written on some message or chat box?
In a question and answer, chat box also is there.
Shrijit, where are you?
Yeah, I'm here. I'm already logged in.
No, you have already logged in?
Yeah.
So you are able to share your screen and your presentation, etc.
Hopefully, yes.
So I don't need to, I don't need to share from here, from my terminal.
But I think I'm sharing from here.
Okay, fine. Please go ahead with that. Okay, now question. What is the question?
In the border area, the rivers will have a finger area. Will be Will it be monitored using high altitude areas surveillance?
I think maybe my audibility is slightly less, so you will have to speak just one. Just 1 second. There is a call from director office. I'll just join. Yes. Hello. 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 हाँ जी, हाँ जी. अच्छा. Okay. Okay. हाँ 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 हाँ. ओके. ठीक है, ठीक है. ओके. I'll just go through that. Mhm. Okay, I'll just go. Yes, there. Now, can you repeat the question for me again?
Yes, sir. In the border area, the rivers will have
border
a
area.
finger area. Finger area. The rivers will have finger area.
In the border area,
the rivers will have finger area. Will it be monitored using high altitude areas surveillance?
there are two things. One is the civilian use, one is the strategic and other uses. So for that, already some other departments are working. But for civilian use, like, disaster, etc., and other purposes, we also do that. But in high altitude, it is definitely covered.
Sir, only this is a question. This only the one question.
Now, question is over?
Yeah, over, sir.
Okay, fine.
Sir, only.
So now my colleague, Dr. K. M. Srijit, will speak on the development of, geodetic imaging of geohazard, especially, let me also introduce him that you will also do that, but he has extensively worked and working on development of methods, approaches, and techniques for, for the seismic hazards, which is very important area for us in the Himalayan region. And very rarely people are doing this kind of work using satellite images, and very important. And definitely today we may not be able to predict anything, but after working a lot, after some years, with lot of efforts, definitely we will come to some, some level of prediction, definitely. So you can enjoy his lecture, right?
Yes, sir. Sir, once again, sir, on the behalf of NIDM and participants, I'd like to convey my sincere thanks to you for taking time for joining with us today. So we are moving to our second technical session.
So, can I leave the meeting right now? I have some other things,
Sure, sir. Sure, sir.
Okay.
Thank you, sir. Thank you. I'd like to introduce our second speaker to our audience. Dr. Srijit, sir, was working as a scientist at Space Application Center, Ahmedabad. He pursued his PhD in marine geophysics from National Institute of Oceanography in collaboration with the Goa University. His area of interest is space geodesics for glacial deformation studies, earthquakes, and volcano process, gravity field of Earth, and azotest, with the spear pressure and evolution of seamounts, ridges, and continental margins. He also received the PR Puruskar Memorial Award from Indian National Remote Sensing Award 2019 and IGU Krishna Medal for 2021. He also published more than 30 research papers in international and national journals. With this, I like to invite Dr. Srijit sir. Sir, the floor is yours.
Yeah, thank you, Gautam. I hope I'm audible.
Yes, sir, you're audible, sir.
Yeah. So first of all, let me thank NDMI for National Institute of Disaster Management for giving this opportunity to talk. And so today I'll be talking about geohazards, how we can use advanced space-based geodetic techniques to understand and to monitor geohazards. So not able to move the slides, so just one second. Yeah, that's good. Yeah. So the outline of the talk is I will slightly introduce what are geohazards and space geodesy. I hope many of the students are also attending. So some of the advanced geodetic technique that we use, like the interferometric synthetic aperture radar or INSAR. So I'll give some basics of that. And the geophysical applications of the INSAR means how we use this technique to understand the earthquake deformation caused by earthquakes and volcanic deformation and the earth crust deformation caused by any anthropogenic reasons as well. So let's divide the geohazards into two sections. The geohazards controlled by the tectonic processes, that includes basically earthquakes, volcanic deformation, landslide, and etc. There are more, and non-tectonic processes or anthropogenic processes like land subsidence due to groundwater withdrawal, then mining, the subsidence caused by the mining, and even an underground explosion can cause the surface deformation that we can study using the satellite geodetic technique. Now, another important question is that whether some earthquakes could be triggered by climatic or non-tectonic processes. Yes, indeed, it is true. So this division is not truly to divide into two sections, but there are some interlink between them. Also, I'll show you some examples in the due course and how some non-tectonic factors affects the causes the earthquakes and so on. So this is a very basic thing is the plate tectonics. Many of you must have studied in your school or in the college. So that's the basics of to understand how the earthquakes are happening. So the plate tectonic theory developed in the 1960s says that the outer surface of the earth is divided into lithospheric plates of thickness almost 100 kilometers that include both continent and oceanic crust. And these tectonic plates are not stagnant, they are in constant motion, and we have plate boundaries of different kinds, like the ocean, mid-oceanic ridges. In the mid of the ocean, we have the divergent boundaries, and at the subduction zone, one plate goes to the other, and that causes the subduction. You can get the volcanic eruptions and even earthquakes as well. And the right side image shows how the global plates move from the geodetic measurements, from the GNSS measurement. The arrow shows the direction of the plate motion. You can see the Indian plate moving in the northeast direction towards the Himalayan. I'll come back to that later in this talk. So, why it's important to understand the earthquakes? Because as you know, you all may be knowing earthquake is a sudden burst of energy along the fault systems. And these are two images in the up and the lower side of the slide. You can see in the upper portion, I have plotted the plate boundaries in green and the coastline is in the red. So you can see, for a reference, I can talk. This is the Indo-Australian plate, and the picture in the bottom side is the earthquake epicenters. So you can really correlate wherever there are plate boundaries, we have the earthquakes. Because the plates are in constant motion, that's in friction, and when the earthquake can mostly they are co-located to the plate boundaries. So it's extremely important to understand the plate boundaries to measure what's going on there in order to understand how the earthquake is happening there. So it's not only just to study or monitor the earthquake, we need to understand the science or the physics, how earthquake is being generated. Now, one of the classic theories of earthquake is the earthquake deformation cycle based on the elastic rebound theory. So that suggests that earthquake is not a very sudden phenomena, it's a cyclic process. So in the green three blocks have been shown, and in the bottom it's showing the years. So it's a fault, the red dashed line is a fault, and the stress is being accumulated for almost 200 years that deform the crust, and at some point of time, it slips or it gives an earthquake. So there are three different phases: an interseismic period where slow deformation is going on or stress being accumulated, and so that deforms the crust, and there is a coseismic period where there is a sudden release of energy or it's an earthquake that slips the fault to a few meters, and again it goes back to the interseismic period. So if I plot it together, the strain or the deformation in the y-axis and the time in the x-axis, you can see for centuries it accumulates the strain, and then one fine morning it releases, giving a few meters of deformation, that's an earthquake, and again there is a slow relaxation, that's a post-seismic period, and it goes back to the interseismic period. So this is the reason why we get repeated earthquakes on a fault, on the same fault. So the way we understand an earthquake depends on how the stress is getting accumulated on the fault and how it deforms the surface manifestation of this stress accumulation is the deformation of the earth. For an example, from the field, you can see the 1906 San Francisco earthquake created a huge offset of 2.5 meters. You can see the fence, it was continuous here, created an offset. So this is a typical coseismic offset. So today we'll be talking about how we use the space geodetic technique to understand different stress accumulation phase on the fault systems. So here is an example. So as we all know, the GNSS is a space geodetic technique that is widely used right from your navigation aids in the car. You can see the GPS, and these are geodetic class GPS systems which can monitor millimeter level deformation in the earth crust, and there is a global distribution of the GNSS or the continuously operating reference system, that's tools that can monitor the earth crustal deformation. So one example is shown for the seismic cycle here. This is from the Nepal, Kathmandu. You can see a time series from 2004 to 2020, which record three components of the deformation: the east, north, and up. And you can see the 2015 Nepal Gorkha earthquake, how it is, how the deformation really happened over the surface of the earth. It's almost a meter deformation. So the GNSS is a method we can understand both the three phases of the earthquake cycle: the interseismic, which is shown here in this period, the coseismic, and the post-seismic. So the left top map shows the strain rate map derived from the GPS distributed over the globe, and the right shows again the strain rate in terms of second invariant of the strain. So you must have noted that there is a huge data gaps in the GNSS. You can see the whole this region, the China and the Russia or even the India, we have very few GNSS stations which is open for the research, so that we can understand the strain developing over there, and it's highly difficult to maintain because we need huge instrumentation on the field to maintain the instruments. So I'll talk about how there's about an advanced space geodetic technique that's called the interferometric synthetic aperture radar in the next slide. So this is basically a satellite-based system. It's a satellite-based radar. As you know, radar in the red shown is a radio detection and ranging. We send a pulse and get back the pulse, and using the velocity of the light and the time ranging, we can understand how far the object is. This is well-known technology. So the same radar mounted over a satellite can send pulses in a side-looking geometry for getting a wider swath and receive back the sequence. So that has information, the ranging information, and the phase of the signal is very much useful. I'll come to that in the next slide. So a radar image. So if we take a radar image from the satellite, it has an amplitude and it has a phase because it's a complex parameter. So it's a collection of echoes in a complex parameters. Now, the phase is a very useful information. So as you know, the left image shows an interferometric setup that is called the Young's interferometric experiment. We have two S1, S2 coherent source, it produces an interferogram. So this is the +2 science that we must have studied. So if you apply the same technique here, we have two radar images acquired in slightly different geometry from two satellites, or it should be same satellite coming into the different position after some time, separated by a baseline. So you can produce a similar kind of interferogram. So that interferogram is sensitive to the topography, and because the interferometric fringe depends on how far from the source is. So it is sensitive to the topography and the change in the topography. So how we can, so if you remove the topographic component from an interferogram, literally you can map the deformation case by the earthquake or any other process using this technique. So if you have two SAR data, one before the earthquake and one after the earthquake, so there is a deformation and there is a phase change caused by the earthquake. That phase change we can precisely map, and we can map the deformation caused by the earthquake. So here is an example. So the phase is rad between -pi to 2pi. So we have to, if you can count from satellite moves from here to here, and there's an interferogram. So if you count the number of fringes, you can see the density of the fringes increases near to the fault. That says that one part is deforming more, and if going away, it shows the opposite direction. So by counting the number of fringes, or you can mathematically unwrap the fringes to understand, to make a map of the deformation caused by the earthquake. So this technique is developed in 1990s and has been widely used for earthquakes. And in the recent years, we are using the many new satellites like the Sentinel and the ALOS. The technique is widely used, and in fact, we have been working for some time. And I'll be showing some case studies where we have applied this technique to understand the earthquake processes. So this figure, you must be very much familiar with the seismic zonation map of India. And we can clearly see that the zone 2 to 5 is the different class of earthquake hazard, and you can see that the zone 5 and 4 are in the Himalayan region and in the Kutch region are most vulnerable to earthquakes. And there is no zone 1, by the way. That means no part of India is free from seismic hazard. So it's extremely important to understand the fault systems and to monitor them. And your remote sensing of the SAR technique gives a wonderful way to do that. Yeah. So now let's concentrate on the northern part of the Indian plate, where the Himalayan plate boundary. As you must be knowing, the Himalayan plate, it's a plate boundary. The Himalaya was formed when the India collided with the Eurasian plate. Started something around 50 million years back, and you can see the plate interface. The lower image shows the plate interface where India plate moves down, or it moves down below the, or subduct below the Eurasian plate. And because these are the rocks, hard rocks, that's about friction. So at some point of time, it got locked, and that has given rise to the upliftment of Himalaya that is still going on. So Himalaya uplift is still going on few millimeters per year, and this process is continuing. So this is the major cause of earthquake in the Himalayan region. So as I explained in the graphically, the locked portion of the fault where the stress is increasing can cause earthquakes. So the left image shows the magnitude potential at different parts of the Himalayas. As you can see, most of the Himalayan region, the earthquakes of more than 8 magnitude is very much possible, and especially the central Himalayan gap. And as I said, it's a cyclic process. So once the strain is completely released, it takes another few hundred of years to revisit by an earthquake. So the seismic gap, or in the violet region, shows there is almost 700 years of strain accumulation in this region, that is in the Indian Himalayan side, which is not yet released, could be released at any time, giving a very major earthquake of magnitude 8 or so. So you can see the 2015 Nepal earthquake, it did not release the complete energy or the complete strain. It has partially causing the rupture. Again, the earthquake hazard is not completely ruled out for another, and it may be giving another earthquake. I'll come back to that later. So one point is that plate interface between the Indian plate and the Eurasian plate is called the main Himalayan thrust, or it's a fault. It's a very long fault along the Himalayan arc, along which the convergence is happening. So the majority of the stress is getting accumulated at this plate interface. Okay, I'm sorry, there is some technical lag in changing the slides. I think I'll come back. Okay, so yeah, and so the Himalayan earthquakes are of two kinds. As I said, there are earthquakes which cause huge magnitude of 8+ magnitude that cause the frontal rupture. That means if you take a cross section across the Himalaya, you can see the Indian plate. So there are earthquakes with magnitude 8+ shown in the violet that causes the rupture all along the plate boundary reaching to MFT. And we have partial ruptures like the Nepal earthquake, which has partially ruptured the plate interface. So the complete rupture takes another few hundred of years to regain the strain to give another earthquake, whereas a partial rupture could be revisited by earthquake. So it's extremely, the point here is extremely important to understand what's really going on along this fault by measuring the deformation, because all this process, the surface manifestation of this is the deformation that we can measure from the satellite. Now, let's look at the latest earthquake, large earthquake in the Himalayas, that is the 2015 Nepal earthquake. As we all know, this was a very destructive earthquake of 7.8 magnitude, and almost it killed more than 8,700 people and injured, and it's a very destructive earthquake. So it's extremely important to understand how this earthquake had happened. So because if you want to know or to predict, I don't say it's predict, or to understand some kind of warning regarding the earthquake, we need to understand what really happened here and what's going on here. So, and space geodesy gives very good technique for that. And INSAR, there's a proper, the INSAR is a technique not only study the physics of the earthquake, but it's used for the disaster management as well. So here is a damage proxy map created using the INSAR technique, because the surface changes before and after the earthquake gives a kind of decorrelation in the INSAR. So that's an indicative of the damage caused by the earthquake. So this is a operational product where we can map the regions where maximum destruction has happened. So the red and the yellow regions or the violet regions are the regions where maximum destruction has happened. That's an INSAR product in terms of damage proxy map. And again, it can map the landslides caused by the earthquake. There is also very much important in disaster management. So there are LOS data in the Nepal region before and after earthquake, and how it has triggered a landslide is shown here. It is verified using the optical data as well. So these are some of the operational applications of the INSAR rather than studying the science behind the earthquakes. So moving forward, so I talked about the interferograms, or how we can use the INSAR techniques. So here again, it's a Nepal earthquake. The wrapped interferogram is shown over here. You can see the Kathmandu over here, and the earthquake happened somewhere around in the Gorkha region, and but the maximum destruction occurred in the Kathmandu region. The reason is very simple. So the middle image, or in the blue and the red, are a deformation map created from the interferogram, which suggests that the Kathmandu region has uplifted almost 1 meter, and there is a subsidence in the other way, the other side of the Kathmandu towards north, shown as the blue region. So this map itself says that even though the epicenter is somewhere far in the Gorkha region, the deformation is maximum in the Kathmandu region, and we get maximum damage due to the earthquake in this region as well. And the extreme right image shows the 7.3 aftershock of this sequence that happened few days after the Nepal event. So this is this kind of precise measurements, and it matches well with the GPS measurements. So here the advantage over the INSAR is that we can take an image of the entire region and map the deformation, the extent of the deformation. So that's important to understand the science of the earthquake processes and the destruction caused by the earthquake as well. So moving forward, so again, I talk about the seismic cycle here. So this picture shows the post-seismic images of the earthquakes. But you can see that the post-seismic, there is a 1 meter upliftment, and in the post-seismic period, these are different periods. After a few months after the earthquake, the deformation has a reverse sign that shows the relaxation or the post-seismic deformation. What I explained in the previous slide, how the earthquake behaves like that. So it's important to monitor the post-seismic movement, because to understand whether this earthquake would trigger another earthquake or not. So using the surface deformation measurements from the INSAR and from the GPS, we can understand the plate boundary or the main Himalayan thrust, the slip on the fault. I mean, how much the fault has been moved during the earthquake. So that is by using a mathematical inversion of the surface deformation data, which shows that the left image shows that there is almost 5.5 or 6 meter deformation or the slip on the fault in this region. And we can see that the entire slip is in the towards north, and there is no surface rupture. That's the reason why there is no surface offsets created by the earthquake. Those are very minor, but the fault has not, even the rupture has not reached the surface. And again, it's an alarming thing that the complete energy is not released. So this portion towards north, the main frontal thrust, could be revisited by another earthquake. So that's something very important. Even though there is 7.8 magnitude earthquake during this, there is still unreleased amount of strain, and in the post-seismic period, very few. The energy release, the regain is very less, and still the fault is locked. So this earthquake created many questions. That what controlled the rupture, why it did not rupture the entire area, and where the next earthquake could be. So we tried to look at these problems by the interseismic slip rate, or the before the earthquake, what was the deformation going on in that region, whether it can give some clue to the nature of the rupture during the earthquake and what will happen next. So we tried to map the stress and strain prior to the 2015 earthquake using something like 20 years of space geologic data, both from INSAR and from the GPS. So in the left image, the blue arrow shows the deformation. The average deformation in the scale is 10 millimeter per year from the GPS, and we have few INSAR tracks where essentially the GPS measures the horizontal deformation, even though vertical is also possible. But INSAR is more sensitive to the vertical deformation. So I talked about how Himalaya is rising. So you can see two images on the right where you can see that the uplift of the Himalaya is something like 10 up to 10 millimeter per year, 6 to 10 millimeter per year, along a profile it is shown here. So these are the data before the earthquake, which can give the stress and strain before the earthquake, what really led to the earthquake. So here is the analysis. So using this data, we have again done a mathematical inversion to produce a interseismic coupling model. The red and blue shows, the red region shows before the earthquake the locked portion of the fault. So you can see that towards north, south, you have the entire fault is locked, and earthquake can happen only in the locked portion of the fault because it's a brittle failure. Whereas in towards north, that because it's deep and we have more ductile nature, and you can see the blue region has low coupling coefficient. So this tells you that, and here is the rupture plane during the Nepal earthquake. So we can see that the interface is very much important from the locked portion of the fault to the creeping portion of the fault, where the rupture initiated actually. But in fact, if not traveled to the south, then the magnitude would have been much more. And another important aspect is the strain and the B value. The strain rate is estimated using the GNSS measurements, which shows that there are two strain patches, one to the west and one to the east, and the eastern portion was released by the 2015 Nepal earthquake, and all these data are again I'll tell you before the earthquake. So this portion was released during the 2015 earthquake, and there is an unreleased strain development in this region. So that can cause another earthquake of similar magnitude. As an independent check to this observation, we looked at the B value. B value is derived using the seismicity data. So the low B value or the blue region shows high stress accumulation again prior to the earthquake. So again, it shows that there are two regions, but where the high stresses are there. One is released by the earthquake in 2015, and there is unreleased stress towards the west. So all these studies suggest that there is unreleased stress or strain towards the west of the epicenter that could be revisited by an earthquake of similar magnitude. So the same thing, if you put together even though the Nepal earthquake has released some energy or some stress is released, still it can have a earthquake towards west. And the 1934 and 1905 we have shown is the past earthquakes. So those are believed to be complete rupture, and this region has been accumulating strain for several years, for hundreds of years, and a portion of the energy is released during the earthquake, but still it has unreleased portion of the energy. That's really important to understand the seismic hazard, because it's equally important that we should understand where the earthquake can happen rather than when it can happen. That's a very difficult question to answer. But this kind of studies could lead to give some clue on the portion where the portions where we can expect an earthquake. That's important, the seismic hazard. So this is our another study. Recently, 2019, there was an earthquake in the Mirpur region. And again, beautifully, it has captured by the INSAR, you can see, and again, it's a 6 magnitude earthquake. So it's not that destructive as you can say the Nepal earthquake. And you can see the deformation around a few centimeters. There in Nepal, it was around a meter, and here it is a few centimeters of deformation. And again, this earthquake is scientifically somewhat interesting. So we use this data to understand the slip on the fault, and using the inversion, and try to understand why the earthquake happened here. So because this earthquake happened on the southern end of the fault, whereas you can see the Nepal earthquake happened here and ruptured all the way here. But this earthquake locally released the strain because the entire fault is locked, but one portion was locally slipped. So again, one interpretation is that there is a local weakening of the fault that must have triggered earthquake. Again, it's important in hazard assessment as well. If there is local weakening within the fault region, it can create a series of earthquakes of magnitude 6, or whether it can lead to a mega thrust earthquake which can rupture all this region. That's important to understand in terms of earthquake hazard. So, and another important thing is the stress transfer that must have caused by the earthquake. So we have computed the stress that must have caused by this earthquake. So here it is shown the stress in terms of bar due to the earthquakes. What we can see is that the nearby faults due to this earthquake are under pressure, or the stress is increasing. And again, it's a question how in future it could be released, whether it could be released in a creeping way, then it's much safer, or if it can give another earthquake of similar magnitude. That's the question It's an open question, in fact. Now, again, I'll tell you about another earthquake. That's a recent earthquake happened in the Assam. So this earthquake is of having a different nature. It is a deep earthquake, and there is no primary fault or primary surface deformation recorded as expected, because it's a deep earthquake of almost 30 kilometers within the crust. But this earthquake happened in the sedimentary tract of the Brahmaputra river. There we have the loose soil. So it has created a lot of surface offsets. You can see the liquefaction, the what change in the water level. So we have observed from the field, it's a collaborative study with the GSI. So we have observed that during the earthquake, the water level in the wells increased, and after earthquake it has gone down. And in the similar way, there are rivers that got flooded during an earthquake, and there are local offsets. You can see 15 centimeter offset mapped on the field. For such offset, we have also mapped using INSAR as shown in the middle image. So this shows another example how we can use this space-bound technique to map the local features during an earthquake, because this is again important, because if the local offsets are important, because those are weak zones where it has to be taken care of during the future constructions. So I talked about the change in water level in river during the earthquake. So we try to map that using the coherence properties of the INSAR. So the left top image shows the before earthquake coherence, and after during the earthquake what is the coherence, the difference map is shown. So what we can see is that all the tributaries to the Brahmaputra, here this is the Brahmaputra and these are the tributaries. The earthquake happened somewhere around here. So the earthquake has caused water flow in all the 5 tributaries of the Brahmaputra, not in the Brahmaputra itself. So this is a change detection map. And another evidence of this is the normalized water difference index created using in the optical images, which shows that few days, so a few hours before the earthquake, the river was dry, and few hours after the earthquake, you can see the flooding of the river in the blue. It's one of the rivers, and again after a few 10 days or so, it again got dry. So here we are trying to understand how the earthquake is affecting the surroundings in terms of how it is disturbing the hydrogeological section of this region. So we postulate that the pressure difference caused by the earthquake must have created this kind of phenomena, how it is affecting the hydrogeology of this region. Yeah, so in the beginning, I talked about the non-tectonic forcing of an earthquake. So here is an example. That is it's an ongoing earthquake. Swarm is going on in the Palghar region, south of Bombay, where you can see hundreds of or thousands. In fact, it's in thousands. Almost 20,000 earthquakes have already occurred over a small region of 5 into 10 kilometers square, and nobody knows how the earthquake is happening, because that's why it's called a swarm. It's not a main shock and aftershock. It's a series of earthquakes, and it is kind of distracting as well. And it's happening since almost 4 years with some breaks in between. And we took some INSAR analysis, and here is a time series INSAR analysis which shows that exactly where there is a huge number of earthquakes, there is a subsidence going on. Again, so that really means that there is a triggering either due to a fault or due to some other reasons. So that's a very interesting science question. So again, we did some modeling how to understand what's really going on here. So there are two options, whether it is a tectonically driven or there is a slip on the fault. So that option, yeah, there is a slip on the fault, but it is not tectonically driven because it is a stable continental region. It's away from the plate boundaries. There is no active fault in this region. So we postulate that it is due to the monsoon triggered or due to hydrofracturing, because of the water percolating deep into the crust can trigger the earthquake. So this is a typical example where we can see an earthquake or series of earthquakes are caused by the hydrofracture or the movements of the groundwater within the earth. It's interesting to note that the energy or the geodetic moment, in terms of geodetic moments, the energy, basically the energy caused by the earthquake from the geodetic measurements or from the INSAR, which says it is around 5.8 magnitude, but from seismological observation, the cumulative energy is something like 4.5. It's a huge difference in the logarithmic scale. So that clearly says that non-tectonic factors are controlling or that is creating the deformation, and that's controlling the earthquake over there. So this is the interaction between the tectonics and the non-tectonic process. It's an example. Now I'll leave the earthquakes and let's take another interesting topic, that's the volcano. So as we know, India has only one active volcano, that is the Barren Island, that's located in the Andaman Sea. This volcano has been active for 1991, and before that it was dormant for almost 150 years. So there is a cinder cone where the volcanic vent is there, and these are the lava deltas. So there are two lava deltas on the north and the west. Those are created by the lava flow from this cinder cone. So we took an INSAR survey to understand what really how thick is the lava, and from where the lava is coming, or the source of the magma source. So here it shows two images. These are mean deformation from 2007 to 2010, and another image showing mean deformation from 2015 to 17. And here it shows the time series at 2 points, how the deformation evolves with time. And to the extreme right shows the vertical and the east-west component deformation derived using the INSAR method. So which shows that there are two kinds of deformation going on. The deformation at the lava field or the lava delta is due to the subsidence of the cooling of lava, because the lava, when it gets solidified, it becomes heavy and it subsides. That's a continuous process going on. But whereas in the cinder cone, the deformation is basically caused by the volcanic processes or the subsurface process or the magma flows. So we did a model to understand from where the source of the volcano. So we find that the depth to the magma is somewhat very shallow. It's around 600 meters. So the bottom left image shows how the volcano is being driven by the subducting Indian plate. So the melt is going up, and there are multiple. It appears to be there are multiple magma reservoirs, one at the deeper level and the very shallow level, that we could get from the INSAR measurements, and which is triggering the earthquake for a long period of time. And INSAR could also be used to measure the change in topography over time. So that essentially tells you the topography of this island changes because of the lava flows. So using that technique, we could map the lava flow thickness at two different time periods. 1979 to 2000 shows around 60-meter lava, and after that you can see here in the top right image showing the topographic change depicting lava flow thickness from 2000 to 2017. So this tells you how the topography of the island evolved with time. So a profile A dash, that's around here, you can show how the 1979 topography, and over that there is a deposition of the lava, and then still it is going on. So in terms of hazard, it is away from any settlement. It's safe because it's a very active volcano. That's very interesting science topic which has to be studied. Now maybe coming to the conclusion, just by saying one more process, that is the groundwater withdrawal. So because as we know, the GRACE is a sensor which is pretty popular now. It shows that the Indo-Gangetic Plain and the Punjab region has subsidence due to the extraction of the exploitation of the groundwater. So here is a study to combine the GRACE observation and correcting it with the GNSS observation to map the subsidence over the northern India, which shows that the Indo-Gangetic Plain shows subsidence, that is shown in the blue region, which is caused by the unsustainable consumption of the groundwater basically for the irrigation purpose. It's not only the Punjab region, which shows again subsidence in huge, but even in the Indo-Gangetic plain also, there is a huge subsidence due to the groundwater. Now, this is the final thing I want to show. So, I've been talking about the natural processes, now the natural hazards. So, the INSAP would be also used to map any kind of huge deformation caused by kind of explosion. So, this is an interesting study that we have carried out for the 2017 North Korean nuclear test. As you can see, it was carried. These are the past nuclear test site, and so the question here is that whether we can estimate the yield of the nuclear explosion or nuclear test using the INSAR technique, because it's a remote sensing technique. You don't need to go to the field, you cannot go to North Korea to measure this. And the other method is the seismic method. There's a far field method, and we have tested it. These are the deformation caused by the nuclear test before after image in two different directions is shown. And we model we try to estimate the yield and the source depth of the earthquake, which shows around 245 to 271 kiloton of the TNT equivalent. That's around 17 times what is used for the Hiroshima, and source depth is around 500 meters. So this is a topography. You can see that there is a topography. They put a tunnel over here, and this is the cavity that would have caused by the nuclear test, and all these are estimated using some assumptions of the physics using the surface deformation measurements. So this is just to because it's very similar to a volcanic explosion. How a magma chamber can give an explosion. The similar kind of theory has been used here to estimate the volcanic heat, the volcanic source properties. So I would conclude here is that the space geodesy, in particular INSAR, has a great potential to probe the tectonic and non-tectonic deformation processes, and that's very much important in geohazard assessment. And the physics of the earthquake, especially the generation process, the strain accumulation, need robust and long-term measurements. So that has to be continued. And dense geodetic, both INSAR and GNS, are required for the study. So I'll conclude the session just by briefing about an exciting new mission that is being made jointly by NASA and ISRO. So that's called the NASA-ISRO Synthetic Aperture Radar mission that will be commissioned in 2024. So this is a very special mission which can produce deformation, or which can produce the deformation map globally with uninterrupted time series, and at a 12-day repeat cycle, the entire globe will be covered with a very huge swath of 240 kilometers, and it's a dedicated mission to understand this kind of process, both the earthquakes, volcanoes, landslides, and all this kind of process. And we are working for this and excited to be for the launch of this mission. And another important thing is that this mission has a very open data policy and ready to analysis data. That means we don't need to process the interferometric because it's a very complex processing. So as a part of this mission, freely the data interferometric products will be freely available for everybody to download, and it's going to be an exciting mission both for disaster management and for the science as well. So I conclude the talk here. Thank you very much, and I'll be happy to answer some questions if you have. Thank you so much.
Sir, thank you, sir. Thank you, sir. With your permission, we will take a couple of questions from the audience.
Yeah, is there anything in the chat box?
Yeah, sir. Only one question. Sir. One question is there. Does the government of India have any policies so that before starting the borewell by any farmer, your department is consulted, and the area of water-rich area is suggested by your department to dig a borewell?
Sorry, here. I mean, 1 second. Let me read. Yeah. So what's the question? Let me check the question myself because I'm not hearing you properly.
Okay, sir.
Does the government of India have any policies so that before starting by any farmer, your department consulted at the area of water? Okay, so there are different departments which are concerned with the the groundwater policies like the Central Groundwater Board and other areas. So they have bore wells, the experimental bore wells as well as the regular monitoring. And ISRO is not an agency for that, but these are basically okay. We have done many projects on the groundwater exploration, but at a larger scale, because using satellite we cannot go to a village or very small level scale, but at a larger scale we have done. But as such, we are not the authority for any government organization to consult before going for a borewell also.
So only these are the questions from the participants.
Yeah, sure.
So on behalf of NIDM and participants, I'd like to convey my sincere thanks to you for taking time for us to deliver training session on geodetic imaging for geohazards. Dear participants, this is the end of today's training session. Before concluding today's session, I'd like to convey my sincere thanks to Sri Taj Sir, IPS CD, and Professor Prakash Sir, Head GEMA Division and CBR and Industrial and Cyber Division in NIDM, Ministry of Home Affairs. And also my heartfelt thanks to Dr. Bahuguna Sir and Dr. Shijit Sir, and also the panel members and participants. A very special thanks to IT section of NIDM who is working behind the curtains. We will meet again tomorrow at the same time, and you can also join tomorrow's webinars with the same link. Thank you all. Jai Hind.
Thank you.
Thank you so much, sir.
Yeah, thank you. So I think I can leave now.
Yes, sir, you can leave, sir. Thank you.
Yeah, thank you so much.
So, dear participants, tomorrow we will meet with another training sessions from inquiries as well as from the NIDM. So, please join tomorrow's sessions with the same link and at same time. So, we will meet tomorrow. Thank you so much. Jai Hind.